All right, so let's talk about spatial vision today, right? This is going to be exciting. We've previously talked about, when we've talked about vision, we've talked about the physics of light itself, right? So that's been pretty awesome. We talked about the structure of your eye and the nervous system. So we talked about some visual physiology, right? We talked about on and off center receptive cells, things like that. Last week we talked about color vision. You guys took a bunch of color vision tests, so that was great as well, right? So that's been a lot of fun. This week we're going to talk about spatial vision. Now this says chapter 8. This is because it's from the second edition of the book. For those of you that have the third edition, this is chapter 9, right? Because the color vision chapter was ahead of that. All right, so we've got some learning objectives. The first thing we want to do is we want to step back for a moment and we want to review just a little bit of information that we talked about when we talked about that visual physiology, right? Because we talked about different types of receptors. You guys remember we talked about rods and we talked about cones, right? So we have rods and we have your cones. And we said these guys are responsible for two different kinds of vision, or vision under two different criteria, right, or two different sets of light. One is what we call scotopic vision, right, which kind of means low light levels, right? And then the other is photopic vision. That's when light levels are really high. So that's like in a room like this. Basically, this is photopic, right? If you're outside, that's going to be photopic during the day. If you're outside, sort of in those like, you know, from dusk to dawn period, that's going to be scotopic vision, right? You wake up in the middle of the night, all the lights are out in your bedroom, anything that you can see is going to be mediated by scotopic vision, okay? So, we know rods, you've got a bunch of these, like 120 million, right? They're all over the place, all in the periphery. Cones, you've got about 6 million, they're all jammed in that one spot in the middle called the fovea, right? So they're all isolated there, we talked about that before. That's where you put things when you want to read them. When it comes to light levels, this is what's sort of important. This measurement is candles per meter square. I don't want you to really put your head around that too much, right? Because Chandler's just going to get a little confusing, right? Because you're thinking like, why do I need to know how many candles I can cram into a square meter, right? You're not trying to put out like a, you know, a Bath and Body Works display table, right? So you're not like measuring how many candles you have there, right? This is the light that would come from a standard candle. You know, how much of that's going to fall on a square meter of space? How many of those photons at any given time, right? It's kind of what that means. I don't want you to think about it too much. Those rods will pick up light anywhere below 0.01 candles per meter square, right? So that's like 1/100th of a candle, right? So it's like this small bit. In order for you to use your cones, you have to have 10 candles, so you can imagine it's a lot brighter, right? So we have to have something much brighter. Color vision, we talked about that last week. It's all handled by your cones. Don't worry about the peak spectral sensitivity, but for our purposes today, one of the things that we really want to focus on is what we call spatial, and briefly we'll talk about temporal sensitivity, right? So when we use the word spatial, we're meaning how are things arranged out there in the world for you, right? So how many of you remember 2 weeks ago we took a vision test, right? You guys did phenomenal on that. You could all read the E at the top, right? So we took that vision test, and really what we were measuring there was how good are you at spatial vision, right? How many white and black bars can you resolve in a given amount of visual space, right? And so as we made those dark and light bars smaller and smaller and smaller, it became harder for you to see, right? And as you think back to the structure and how your cones and rods are distributed in your retina, it's about the spacing of those, right? Remember, guys, we talked about the inner receptor angle, right? And we said, you know, the farther your receptors are apart, the bigger that receptive field's going to be. We can pack more receptors in, then you can use more receptors for each degree of visual space, right? You can get a higher resolved picture. This is like playing Super Mario Brothers on the original Nintendo and playing Call of Duty on your, you know, your Xbox One, right? So as we get more and more, you know, sort of pixels, more and more receptors, we get a much more resolved picture, okay? Much better, better idea. This CPD measurement, we'll see this a lot. That means cycles per degree, okay? So what is a cycle? If we're talking about dark bars and light bars, right, we've seen that, and I'll show you some later. A dark bar and a light bar, that makes one cycle, right? Okay, so dark bar, light bar, one cycle, another dark bar, another light bar. Mary, that's another cycle, right? Degree is degree of visual space. Remember, we can see, you know, like 178, 180 degrees sort of around. So if in your entire visual world you had one giant white bar and one giant black bar, that's not very good, right? Okay, because that's really one cycle per 180 degrees, right? So you have to do the math and figure out what that is, right? But if you get it down to where you have a black bar and a dark bar per degree, then that's not so bad, right? This should tell you, this simple number right here, should tell you why we read with our fovea and not our periphery. Okay? So when you read, the print's really small, right? It's like the small print. And so you really have a lot of cycles per degree in that small print, right? And if you put it out in your periphery, you're only resolving one cycle per degree. So you can only see sort of those big letters. You're 3 times better with your cones because you can cram 3 cycles, right, Skylar, into that 1 degree. So you can see sort of 3 times better. You have 3 times better resolution with your cones than you do your rods, right? Because they're smaller, they're crammed in there a little better, and you have better spacing. Does that make sense to everybody? So the higher this number, the higher your cycles per degree, that means the smaller bars, the smaller objects, whatever it is, the smaller you can resolve. All right. All right, we already talked about photopic vision and color. We talked about scotopic and rods. Again, low spatial resolution. Kind of have poor color discrimination with the rods. They are great because they don't require a lot of light. Okay, so they're helpful for that. They're not so great for other things. All right. Now that was a lot to get you into this, but now we need to think about, Olivia, luminance gratings. A luminance grating is probably the most important tool in the toolbox for someone who wants to study vision, right? So let's think about this luminance grating. It's a dark bar, it's a light bar. If that transition is abrupt from dark to light, we call that a square wave. I'll show you a picture in a moment. If it's a smooth transition, so if we kind of go from dark to sort of gray, and then back to white, and then back to sort of gray, and then to black, that's called a sine wave, right? Because it's got that smooth transition in what we're going to call contrast, and we'll talk about that here in just a moment, okay? So, if we want to determine our spatial vision, our visual acuity is another word we might use, we're going to use these luminance gratings. Why would we use a luminance grating and not, I don't know, I'm trying to think of like what would be an awesome picture that you guys might get excited about. What if we used a picture of your bill from Marshall that said $0? That would get you excited, right? Why would we not use like a natural stimulus like a tree or a dog? It's really hard to control those stimulus parameters, right, Keelan? So if we're going to study something scientifically, we want to be able to adjust all of the parameters of that stimulus and then figure out how well you can see things in different parameters, right? So if I have a dog, for example, so how many of you were thinking about a poodle, right? So there's already a problem because it was a poodle. Okay, yeah, I know, right? So you already see the problem if you're using some natural stimulus. We can't really control how do we change the contrast of a dog or the size of a dog or the orientation. I mean, you can change the orientation of a dog. You have to be careful how quickly you do that. They do vomit. So that's just a heads up there. Don't flip your dogs too quickly. If you have a large dog, you can also injure yourself. So watch out for that. But with a luminance grating, we have super control on this, right? And we can control 4 things, okay? The first is frequency. Hey, we've talked about frequency before, right? Who remembers when we did that?
We were talking about sound, right? And light waves.
Sound and light waves. And what were we measuring there? We were measuring how many peaks. We were doing in peaks and troughs, right? Or troughs per second. So we were measuring, again, that's really a cycle. A peak and a trough is a cycle, right? And instead of per degree, because we were thinking about, instead of time, we were measuring it per second. But it's the same concept, right? We measured it in hertz, that's how many cycles per second, right? But we're doing the same thing here. So we can adjust the frequency. I can make those bars smaller, which increases what we call spatial frequency, right? Because I've crammed in more peaks and troughs, more dark bars and more light bars. I can spread that out. I can make that a lower spatial frequency, right? By making those bars, they're actually going to get bigger. So that's awesome. We can control frequency.
Is that how they do contrast and stuff on TVs and things like that? Did I ask that right?
I'm not sure what you're asking. Let's try one more time.
Like the contrast on television, how they separate the lights from the dark. Do you increase that spatial frequency? Something more contrasting, I guess.
That's going to be something different.
I didn't know.
Yeah, what they would do, when we'll talk about contrast, that's the next point that you can adjust. So when we're thinking about contrast, and I want you guys to think a lot about contrast today, because we're going to spend like an hour, hour and a half measuring contrast, right? So it's going to be exciting. So Chandler, when we're doing contrast, what we're thinking about here is what's the relationship between the brightest part and the darkest part of that image, right? And so if you're thinking about contrast, so when you adjust the contrast on your, I know you've probably done this on your computer monitor, right? It's like, oh, I'm going to play around with my roommate's contrast and turn it up or turn it down so they can't see what's on the computer screen. Anybody done that one? It's a great prank, by the way. You should try it. So if you turn contrast all the way up or all the way down, what you've essentially done is you've taken the lightest or the darkest portion of that and the brightest portion, and you've made them the same. And so everything's going to look uniform, some sort of grayscale, right? Somewhere it's all going to be the same. There's not going to be any variation, right?
How is that different from saturation?
On a TV?
Yeah, like a desktop.
Wouldn't that just be the depth of the color? Like how
Yeah,
the
I think
color-
that's more of a color gun sort of issue, right? Just trying to think the last time I messed with a monitor.
Right.
So contrast is the other thing we can adjust with this sine or this square or sine wave grating, right? This luminance grating, which is great because, as we've said, you know, when you turn up or down the contrast, it becomes harder and harder to see things, right? You can't tell the difference between two objects because their luminance values are becoming closer and closer together, right? It's going to level out. So what's nice is we can look at the relationship between spatial frequency and contrast, right? So we can adjust two things at once, okay? Hold on, I'm going to show you how that works. We're going to adjust two things at once and kind of determine what you can see at different spatial frequencies and different contrasts simultaneously, right? The other thing we can change is orientation. What we mean by this is something that's vertical versus something that's horizontal, right? We can kind of put it any angle in between, right? So we can take this luminance grating and we can just rotate it around in a circle. Finally, we can adjust the phase. We're not going to think a whole lot about phase, but what we mean by this is, let's say we have the exact same frequency, the exact same contrast, and the exact same orientation, but we shift the start of that wave, right? That shift the start of the dark bars and the light bars a little bit one direction or the other. And so now instead of lining up dark bars and dark bars, we could actually line up dark bars and light bars, right? And we talked about this briefly, Mason, when we talked about sound as well, because we said if you take a sine wave and then you take the same sine wave and shift it, the peaks and the troughs will cancel out, right? And we can do that with the visual system as well. We can do that with these luminance gratings, okay? Now there is a concept called a contrast threshold. At any particular spatial frequency, there is a contrast value that you need, and we'll talk about how we calculate contrast in a moment. There's a contrast value that you need to see that particular frequency of dark bars and light bars. Okay? Keelan, hang in there. I told you, today's the day. You're not going to know what's going on. It's all going to come together in probably 8 more slides.
So is a lower frequency a higher contrast? Is that...
You can adjust contrast independent of frequency.
Okay, they don't...
And we'll talk about in just a moment, Chandler, there's an interesting relationship. You would think always for a lower frequency, then I need lower contrast because it's like a big thing and a big thing, and I can tell the difference. But when you get to the medium and the high frequencies, there's an interesting relationship. And so just hang in there. All right. Let's hope this works. Let's keep these. Hold on just a moment. Well, that's great. So, Bill Gates has once again stumped me. This was a fun demo that would demonstrate these 4 characteristics of a luminance grating. But this is essentially a luminance grating. We can see this. Is this a sine wave or a square wave? Anybody want to take a guess?
Square.
Anybody else want to take a guess?
Sine.
There you go. Wow. So many people knew that answer, Kyle. Yeah, great job. Why is it a sine wave and not a square wave? Anybody have a guess? So, again, a square wave looks like this, right? On the side. So it's dark, and then all of a sudden it's light, and then all of a sudden it's dark, right? For a sine wave, it probably starts out light, and then gradually gets dark, and then gradually gets light, and gradually gets dark again, right? You kind of see how in the middle here it's really bright, and then as you move over just a little, it's kind of gray, and then it gets a little bit darker as you get to the middle of the next cycle. That's what makes it a sine wave, it's those smooth transitions. So unfortunately, this demo did not transfer well. I can make this available to you on Blackboard so you guys can play with this to have an idea of what we're talking about. But if we were to slide this spatial frequency, so right now it's set at 16, right? That's 16 cycles per degree. Now this is going to change depending on how far away you are from the screen, right? Or how big the screen is, okay? So if you're really close, as we've said, excuse me, that will change the spatial frequency. Remember when we talked about quarters? And we said, I know, I think I'm allergic to you guys. I was fine earlier today.
Would it help you if I told you I smuggled in my cat?
You know, I have cats at home.
Oh.
Although I think I am developing an allergy to them, which is going to be unfortunate for me.
It's okay.
Because I'm going to have to sleep in the garage, I think. But then there's this outside cat that tries to sneak in there too, so that's a problem. So I don't think I'm going to get away from it. I like it better when students bring snakes to class. Most people aren't allergic to snakes. That happened. True story.
There's
How do you feel about
unfortunately-
hairless guinea pigs? If like someone were to have a hairless guinea pig?
Do you have it with you now?
No, but I
Okay.
can bring a guinea pig next time.
No, we don't need it. So, spatial frequency, again, can change, as we move, but let's think about this. If I were to slide this down to something other than 16, like let's make a smaller number, let's make it 5. If I change the spatial frequency to 5 cycles per degree, what's that going to do to this bar size? Is it going to make the bars larger, or is it going to make them smaller?
You said 5 cycles per degree?
Yeah, 5 cycles per degree.
Okay, larger.
Yeah, it makes them larger, right? Because we're getting only 5 cycles in 1 degree instead of 16 cycles, right? So it's,
yeah.
it's sort of the question like, how many of you have, we're getting ready to go to spring break, right? And you guys are going to have a cooler for something, right? And you're going to put some juice boxes in there, right? And so you're going to think, do I want to put in 2 64-ounce orange juices, right? Or do I want to put in, 48 8-ounce orange juices, right? Because you can get them in those little boxes now, right?
I didn't know
guess, I don't know. I don't keep up on the juice box market. I'm just
Do they sell this at gas stations?
assuming you can do that. If anybody knows about
Sam's
juice boxes,
Sam's Club.
buy in bulk.
Sam's Club.
That's where you do.
The point is, you've only got one cooler, right? If you want to put more units in, you have to make those units smaller, okay? So if you want more cycles per degree, right, Mary, you have to make each cycle smaller, okay? So instead of putting in 2 jugs of orange juice, you're putting in, they do sell them in the little pints, right? So you're putting in more of those little pints.
I love this analogy.
So if we were to go up to, let's say, 32 cycles per degree, now what happens to the bars? They get really skinny, right? So they get a lot smaller.
So would that make it very hard to see the?
It's going to make it, in general, as spatial frequency increases, it becomes more difficult for you to see that, right?
Yeah,
and
that transition.
right, because each is going to get smaller, and at a certain point, your spatial frequency is going to get so high that it's going to be smaller. Each cycle, and I have a great slide in just a moment, each cycle is going to be smaller than the size of your receptive field, right? And so you're not going to be able to determine if that's a bar or not. It's just going to look like a gray patch.
I guess that's what I was asking.
Okay.
That's what it would look like if you decreased it or increased it.
Increased it.
Why?
So if you increase the spatial frequency and the bars keep getting smaller and smaller and smaller and smaller and smaller and smaller.
Okay, well, all right, figured out.
Okay. So if we adjust contrast, right now contrast is at 0.5. I'll show you guys how to calculate contrast in just a moment. Basically what this means is the highest luminance value and the lowest luminance value, if you do the math on that and you compare the ratio of those two, it's like a 0.5, it's like 50%, right? If we make this 1, then that means it's as bright as possible and as dark as possible, right? So that difference is 100%, okay? So these lighter patches would become bright white like we have over here, and the dark spots would become, dark just like this lettering, okay? So we increase the contrast. If we decrease the contrast, then things become closer and closer and closer to that same grayscale. Orientation, again, we would just kind of take this patch and rotate it, right? So that's not too big of a deal. And phase, we could just shift it, relative to its current location. So not a big deal there. Questions about those 4 particular parameters? The 2 that I really need you to think about the most are spatial frequency and contrast. Okay? Awesome. Because right now we're going to take spatial frequency and contrast and slam them together. And we're going to come up with something called spatial contrast sensitivity function. And that sounds really complicated. It really does, but it's not. Basically, all we're saying here is, how good are you at a certain spatial frequency given a certain contrast? Or you can kind of do the inverse and say, how good are you at a certain contrast given a certain spatial frequency, right? And that changes. And what you can see here, hopefully this shows up well, yeah. What you can see is kind of this interesting transition. So what we have is a shift, right, in spatial frequency. So here on the left, it's low spatial frequency. And here on the right, it's a high spatial frequency. Okay? So high spatial frequency. And I think we can see that, right? As you move from left to right, what do you see? You see a change in the size of the bars, right? They're very large over here, so we're, so it's a low spatial frequency. We get a much higher spatial frequency over here in the corner. What's also really interesting about this is that we kind of start here at the top too, and we're changing contrast as we go. So here at the top, contrast is really low, right? And down here at the bottom, contrast is really high. Now I have phenomenal handwriting. What's sort of interesting about this is, sort of previously we would have said, hey, lower spatial frequency, you're going to be able to see that because, that makes sense, right? Because it's just a big bar and a big bar. Doesn't matter what the contrast is, 2 big things, I can see that, right? Unfortunately,
the further left you go, you have lower frequency, higher contrast, and then the more right you go, lower contrast, higher frequency.
well, contrast is going to change up and down. So contrast is changing from top to bottom. So all of this up here is low. See how everything up here looks nice and uniformly gray?
Yeah.
That's because the contrast up there is essentially zero, right? Everything is the same. So whatever the bright bar is and the light and the dark bar, they're actually the same luminance value. So there's no difference, okay? As you move down, we start increasing that,
Okay.
we start increasing that contrast.
So frequency is from left to right, and contrast is
Top to bottom, absolutely. So what you see from this is what's a really interesting feature of your visual system, right? The spatial frequency that you can see at the lowest contrast is in fact these frequencies in the middle. You can see these the best, right? Okay. And that's because of the structure of your retinal ganglion cells, right? We talked about the retinal ganglion cells, remember going back in that midget and parasol system, right? We talked about the magnocellular and the parvocellular layers in the LGN. And how many layers do you have in the LGN? You've got 6. How many of those are devoted to those smaller receptive field sizes? There were 4, right? So those are the parvocellular layers. So 4 of the 6 layers are devoted to small receptive fields. So you should be thinking, because the receptive fields are smaller, that means it's going to be sort of shifted in the higher spatial frequency. Those low spatial frequencies are not going to be as good. Now there is some limit on the upper end, Eli, for how high our spatial frequency can go, right? Does that make sense to people? See how we connected that back to retinal and thalamic structure, right? Okay. We might use the word here band pass. I don't want you guys to get thrown off by this. Previously we've talked about something that's high pass. We've said if it's high pass, then it passes through high frequencies, right? If it's low pass, it passes through low frequencies. If it's band pass, there's some band of frequencies in the middle that come through the best, right? And this is band pass because these middle frequencies are the best. And if you take a close look at this, I've got a glare on my screen. There's probably one here. You can sort of see, and I'm just going to make up a line here. Right? Notice there's a bit of a peak. So if you were to follow up, like how high up can I see a low frequency? Well, there. How high up can I see a high frequency? Maybe it's like here. How high up can I see a mid-range frequency? Then it's right there, right? So that shows you you're better at those middle frequencies. Okay. This has some important survival value, right? How many of you have ever been flattened by a battleship?
Not recently.
Not recently. Yeah. So if something is really big, that's going to be in a low spatial frequency, right? Okay. How many of you have been flattened by your brother? Yeah, that's going to. Now we're getting down into that sort of mid-range, right? We're getting into smaller frequencies, things that are more important, right? How many of you have ever been hit in the face with a baseball? Yeah, there we go. Now, see, we're thinking about things that are getting in that mid-range of spatial frequencies. How many of you have ever been flattened by a gnat? Something's that small, who cares, right? You're going to run over it, right? Okay, so you think about those sort of things. It's pretty exciting, right? So we'll put battleships down here.
Oh, words.
Did you want me to draw a battleship?
I didn't know what was happening.
You thought I was going to draw a battleship.
I don't
Letters?
What is that supposed to say?
The vote? You squished the word battleship.
It says, stretch.
It's a battleship with a sail.
That's a dinghy.
It's an old battleship. And then here we'll put a baseball.
Okay, that looks better.
I got to put the stitches on it. And then over here we're going to put a gnat. Let's make a dot. So there you go. Makes sense, right, Tabby?
Where's Chloe when we need to give this wonderful art piece?
Hey, check this out. Here's a graph. How many of you love graphs? Great, Chandler. We have a spot for people who love graphs in the DSM. There, I think, and you could ask maybe our special guest about this. There is a pathological section for people who love graphs, and there's a whole set of issues there, right?
Are you sure about that one?
I'm sure. Trust me. You shouldn't love graphs too much.
Does that represent phobias and mental disorders?
I don't know anything about the DSM, to be honest.
Oh,
It's big, and one of them used to be silver. Is it still silver?
I wouldn't know. I'm just still.
The current one's purple.
Yeah.
Wow. Learn something new every day. What is this graph telling you, right? That's what's important. Okay, what does this graph tell you? And right now it looks to you like, well, I don't know, we've got two boomerangs here, I don't know what they're doing, right? What we're measuring, Charlotte, is, again, spatial frequency and contrast. So basically what we're saying is, at a particular spatial frequency, how much contrast do I need to say, yes, I see dark bars and light bars? Okay, that's what this tells us. Now, we have two sort of graphs here. One of these scotopic, that's for your rods. So not surprisingly, you're not as good there with your rods, right? Because we've already said rods not as good on spatial frequency, so all of that's going to be bad. But let's just think about the photopic section, right? And this is a logarithmic scale, so don't puzzle too much on that, right? But let's go at a low spatial frequency, right? Let's somewhere around, this is somewhere around like 0.2 cycles per degree. That's how much contrast you need for you to be able to see that, right? That's how high the contrast needs to be for you to be able to say, yes, I see dark bars, Laura, and I see light bars, right? If you move on over here to, let's say this is somewhere like, that was 0.2. Here's something like 2, right? So it's a much higher frequency from 0.2 to 2. Okay, it's like a tenfold jump. Look at how much less contrast we need, right? Contrast can be so much lower. Both of those can be much, much closer to the same grade, and we still go, yeah, I can see that. Now, again, it starts to trail off again once we get too high, right? So this is basically what we were showing you in that previous slide, but here we're plotting out the data, right? Now, this fun thing over here is just the inverse of that. So if you'll all turn your heads upside down, you can see that these curves are the exact same shape. So basically, instead of asking you how much contrast do you need at a spatial frequency, we're saying, well, how good are you at seeing a particular spatial frequency given a contrast, right? It's the same thing, it's just, we're just inverting it, right?
So to be able to see those lower thresholds, you need to be a lot more sensitive. Does that make sense?
So if you wanted to see a higher frequency, let me say it this way. If you want to see a higher frequency grading, right, a higher spatial frequency grading, you need more contrast than if you wanted to see a mid-range, right, something between 1 and 10 cycles per degree. That's what we'll consider like a mid-range frequency. Because you see how much less you need, how much more sensitive you are. And that's what that's sometimes why this other graph makes more sense. Because again, if you look from this 1 to 10 sort of range, you'll see, because now it's higher on the graph, you realize, oh, I'm much better at that, right? So it's a little more intuitive sometimes to see it that way. So you're much better, you're more sensitive, right, at those frequencies. If you look at a low frequency or you look off at these high frequencies, you're not as sensitive, right? Which means you need more contrast, which is what this graph over here would tell you. Does that make sense to everybody? So one of these is basically saying, here's how fast you are, and here's how much of a head start you need to beat me in a race, right? They're both telling you the same thing, right? Okay. If I said, how fast are you? And you guys said, well, boy, I could run 100 meters in 12 seconds. Okay, I was like, okay, that's fine. And we can measure that. And then on the other graph, I said, well, given how fast I can run, how much of a head start do I need, or how far behind me do I need to put you so that we finish at the same time? Does that make sense? Because maybe I can run 100 meters or 100 yards, 100 meters in 11 seconds, right? So I need to give you a 1 second head start to get there. And it's basically saying the same thing, but in a different way. Does that make sense? Anybody know how fast they can run 100 meters? Now I'm really curious.
5 seconds.
5 seconds. Yeah.
Teleport.
Sometimes I wish you would make use of that.
Get out my class.
Alex, I actually enjoy that you're in this class. I don't know if you know that. I don't know if I make that clear to you every day. You know what I really appreciate the most, Alex, is you keep me online and on track with posting the lab. Because you're always the first person to tell me Lab 7's not up.
I mean, I'm just surprised that I'm the first person to tell you on Wednesday, the day before it's due. Nobody else is.
Yeah, I am too.
I didn't invite him
We
too,
don't do it
so.
until the day of.
Yeah,
Fair enough.
I'm actually surprised you're the person who's doing it ahead of time as well. But positive steps, we'll take them, right? So, let's think about now receptive fields and spatial contrast sensitivity, right? And why we're sort of better at those mid-range and maybe not, the high or the low end, right? So what we can think about here is those receptive field structures. Now, previously I told you it was center and surround, and we kind of talked about that as an annulus or a donut, right? So we had the center. I'll draw that for you. We had a center and we had a surround, right? And one of those was excitatory and the other was sort of inhibitory going around that. What they've shown you here is they've sort of taken that structure and just elongated it, right? So don't get too wrapped up about it. We've got an excitatory center sort of rectangle and two inhibitory flanks on either side here. Okay? And what we're representing to you here are neurons with small receptive fields and neurons with large receptive fields. And if we wanted to map these back to those retinal ganglion cells and think about those cells in the lateral geniculate nucleus, right? We're thinking about, remember we had midget cells in the retina, and they projected to the parvocellular layers, right? And so they have small receptive fields, so that's these guys here. We also had parasol cells, and those were in the retina, and those projected to the magnocellular cells in the LGN, right? Remember there were only 2 layers of magno and 4 of the parvo. Those are these guys here with the larger receptive fields. So now let's think about us being something in that LGN, right? Either in the magno or the parvocellular layers. Let's think about what these gratings look like to us as a receptive field, okay? This will maybe kind of make some sense. So first, let's imagine we are looking at a low frequency, right? So look how big the white bar, the dark bar, the white bar, the dark bar. I mean, if you were to measure this, and we were to say this square is 1 degree, right? So Emily, we can kind of assume this, right? Let's say it's 1 degree. How many cycles do we have here? How many sets of dark bars and light bars? Right?
4 and 3.
3, yeah, somewhere around 3, right? You might say 3.5 because you've kind of got 4 sort of dark bars, but only 3 light bars, right? But somewhere between 3 and 4. If we measure the other patch here, how many cycles per degree?
12.
12, you already counted. Wow. That's the way to jump ahead. I'll assume that's correct. I didn't bother to count it. So over here we have somewhere around 12. We'll say this is 3. Okay. So, 2 different spatial frequencies, right? We have 2 different size receptive fields. One's going to be sensitive to each kind of patch, right? So let's imagine we're first in that parvocellular layer, and we see this low spatial frequency. What do we see here in the excitatory region? That's just sort of light. What do we see in the inhibitory region? Well, that's sort of light too. Everything I'm seeing is sort of light. So what am I really registering there, right? I'm not seeing any difference across my receptive field. I'm not seeing any change. To me, everything looks uniform. Okay? However, if I'm a larger receptive field, and now my excitatory region, that white bar's falling on the excitatory region, the dark bars are falling on the inhibitory regions, I can tell there's a difference now, right? Part of my receptive field has a lot of illumination, part of my receptive field doesn't have much illumination, right? And I can tell the difference between the two, and I can say, hey, excitatory, inhibitory, dark and light, I can tell that there's something there, right? I can resolve that with that receptive field. We sort of have an opposite story when we go to higher spatial frequencies. if you look at this small receptive field, right? You've got an excitatory region getting a white bar. You've got two inhibitory regions getting dark bars. Okay, so we can tell there's a difference. Different parts of that receptive field are getting stimulated in different ways, right? And that means something. If we look at the large receptive field, what we see is the inhibitory regions and the excitatory regions are both receiving sort of a mix, right? They're both receiving some dark bars and some light bars, but because it's not different across those subregions, it all appears the same, right? We can't tell the difference. It all averages out. Okay, it all averages out to just sort of gray. So your large receptive fields, those magnocellular cells, right, those parasol cells, when they see a high frequency, high spatial frequency object, whether that's a luminance grating I'm making you look at, or it's the words on your page, or it's you're at a distance looking at a forest, right? You see all of the individual trees, right? That's high frequency. They're not really getting too excited about that, right? It's like, well, sort of excited, sort of not excited, whatever. But if we were somewhere and we were looking at something with a lower spatial frequency, right? So let's imagine you are not here, but somewhere else. See, the problem is, like I was going to say, like, when you see mountains. It's not a real fire alarm, was it?
No.
No, that's one of the alarm options.
She's on duty.
Oh, she's on.
Sorry.
Oh, didn't know that. That makes a lot of sense.
I'm really sorry. I'm on duty.
That's okay. That happens.
I'm sorry. Was it a telemarketer?
Yeah, and it's not even an important
telemarketer?
call, so I feel really, yeah.
Oh,
They try to do things to make sure that telemarketers and things don't get this number, so I don't get calls like that.
Yeah.
But it doesn't always work. I'm really sorry.
I was just going to sort of commiserate with you about how frustrating it is dealing with college students. Telemarketers, I don't know. I'd rather deal with them.
You talk to telemarketers?
No,
Yeah, but you can hang up on telemarketers.
Yeah.
Right.
Yeah.
You can't when it comes to that
I can't hang up on you. You're one of my advisees.
Exactly.
I tried.
Yeah.
It didn't work.
Pretty sure you didn't show up in one of our meetings, so that's as close as you could get.
So we're good. So, changes in spatial frequency, different size receptive fields, we're good to go. All right, I'm not going to blow your guys' minds with temporal contrast sensitivity, okay? But there's the same sort of concept when it comes to like how quickly things move. We're going to talk about motion vision in a couple weeks, and I really want to hold off on that when we talk about motion vision, because if I do it right now, like, I don't have enough little cups to catch your brains when they run out, so we're going to kind of bypass that for now, okay?
I appreciate it.
Anytime. But we'll come back and revisit those sort of slides. Okay? All right. I know this is a fun image, right? I know it looks kind of creepy. Everybody's making this face. Like, I don't know why. So, what we've done is, obviously, I love this. In the left, it's a photograph of a face. Just in case you hadn't been following along so far, that's a photograph of a face. Okay, photograph of a face. Now, what we've done is we've taken that same face and we've applied two filters to it. Okay, one is a low-pass filter. Right, so only the low spatial frequencies are coming through. Okay, which low spatial frequencies are coming through which pathway there? Low spatial frequency, large receptive field, talking parasol to magnocellular layers, right? Over here, we have high spatial frequency. It's a high pass, right? Okay. So all the low frequency information has been filtered out. This is information that's going to get those midget cells, which project to the parvocellular layers, excited, right? Because it's the small, fine spatial details. Okay. Now, what you can see from these two images is that they each give us some different information, right? There are different things you can tell about each of these systems, and they're both important, okay? It's pretty exciting, right? I don't know, nobody else is getting really excited about this. all of it together is going to be kind of what you're seeing. Low, high, right? It's just activating two different systems. We have two different systems for different reasons. This is going to become much more apparent again in a couple weeks when we talk about motion. Okay? The motion, visual motion, is going to primarily be handled by those larger receptive fields that are sensitive to the lower spatial frequency, right? Because for visual motion, again, let's imagine a baseball is flying at your face, right? Is it more important to know that there's something coming at your face, or to know that it's an official league-sized baseball from Rawlings? Something, right? Something is because you can get out of the way of something, right? And if you're spending time like trying to read the lettering on it, that's not helpful to you, right? It doesn't really help you. If you think about this from a survival standpoint, is it really important what is falling down on you? It doesn't. Get out of the way, right? It doesn't matter if it's a tree, if it's I don't know, a guy in a bear costume. It doesn't matter what it is, right?
Falling down onto you.
It happens. You get up on scavengers. You know.
Right out of the tree.
You never know. So it doesn't really matter. Okay? So we really want to do that. Now, we've talked before, who remembers that conversation we had about pupil size? Right? And we said, when you're sort of excited, what do your pupils do?
Dilate.
They get big, right? And what happens when things get big? When your pupils get big, you lose, huh?
You take in more light.
Take in more light, but you also increase this point spread function, right? And you're not as able to make those fine resolution, right? So you're not able to sort of make that sort of discrimination. So again, the example I gave you was, if you're running in the woods, does it matter if it's an oak tree or a maple tree based on the bark pattern, or does it just matter that it's a tree and you need to dodge it? Who cares what kind of tree? They're both going to knock you down if you run into it, right? Okay, so you want to dodge the tree. So you're sacrificing something then, right? And you're doing the same thing when we think about these low spatial frequencies. We'll talk about this again with visual motion, right? It's a good example. You're sacrificing some detail to get you out of the way faster. You can figure out what it is after it lands, right? You can pick up the baseball and you can read it later, okay? Or better yet, try to catch it. But it sort of depends on what your goals are. Okay. Does that make sense? In the same way that we took, so I think what's important here, Rhea, is we've talked about these artificial stimulus, right? And we've not really talked about like the real world too much. But we did something similar when we talked about the auditory system. And I started out telling you about pure tones, which don't really exist in the world, right? Because we said, okay, we're going to wait, we're going to have this conversation about timbre in a few minutes, right? And what we said was, you can get a pure tone, that's awesome, but there are all these other little sine waves riding on top of that, right? That make that a particular sound. Even if it's the same frequency, even if it's the same amplitude, if it's made by an oboe or it's made by an alto saxophone, they sound different, right? Okay, because that's the timbre. That's kind of the fun little frequencies that ride on top that give it that individual characteristic. So far we've talked about sine waves, we've talked about square waves, but we haven't really talked much about how that applies to the visual world, right? And how does that actually work? So, a great example is right now I'm looking out into the audience here, right? And so this is a really great example of sort of a collection of sine waves that we've added on top of each other, right? So if I take each individual person and I say, well, you're, as compared to the gray background of those wonderful seats you have, you're different, right? So I can say one is sort of, one contrast and one's the other, right? So two different luminance values. And so if I look out there, and I can see sort of this pattern of sine waves right on top of another pattern of sine waves. So what you can do, in the same way that we could build any sort of sound from adding these sine waves together, right, to make that complicated tone, you can really do that if you think about the visual world and that luminance, those luminance changes, right? So you can take, here's a great example, you can take kind of that lower spatial frequency add it to another spatial frequency, and you can see how you can keep building and building something more complicated throughout this process, right? So you're constantly kind of looking at these changes in luminance. Later we'll talk about other things and how we add this together for shape and object recognition and so forth. But we can take this information, we can add it together. As you see, it's sort of a complicated changes in luminance across a natural scene. And if you look, for example, this might be an example. You're looking out at a forest and the sun is rising over here, and you can see the sun kind of shining on half of your visual world, and the other half is in shadow, right? But there are also luminance changes within that sunlit area and that shadow area, right? So there are these independent changes and then those broader changes across the whole visual world. So everything's just a sine wave. Everything you're looking at, you can decompose it down into these luminance sine waves, right? Because you can work backwards. You could say, well, here is the luminance profile of the image I'm looking at. Let's pluck out a sine wave first, and let's pluck out another sine wave and another sine wave until we get down to these fundamental, and I mean fundamental in a different way now than I did when we talked about fundamental frequency with audition. We get down to that sort of fundamental image.
Does that affect like our depth perception? Is that kind of where that comes from?
Yes, but I don't want to talk about it. I don't want to talk about it because we're going to do depth perception in a couple weeks. Next week? Next week we're doing depth perception. But this is the this is why spatial vision is so important. And you really need to understand spatial vision, because if you don't, depth perception is not going to make a lot of sense. Visual motions are not going to make a lot of sense, right? This is the fundamental capability of your visual system that these other capabilities build upon, right? So they're all going to build on this spatial vision. So you really need to get a handle on these sine wave gratings, on this contrast business, right, which we're going to explore a little bit more later, and so that we can really think about, how that works and how that all fits together. Does that make sense? That was a great question, and you're right on it. All right, and here we go. Here's that fun thing we talked about, the Fourier analysis. I know somebody's had that tattooed on their body or named their band the Fouriers. There's so many ways you could spell that too, right, Mary? I mean, that's such it's a word that's just built for puns. That's what we should do. We should start a band like a barbershop quartet called the Fouriers. Let's spell it F-O-R-Y-A-H. Yeah, nobody thinks that's as funny as I do.
I think it's pretty.
It's brilliant, isn't it? Yes. I mean, it really is. I don't know.
Can I be in 4 years with you?
Absolutely, absolutely. Yeah, we got one more back there. We've got 3 yays. We can get another one.
Your songs will teach people the basic principles of sensation and perception.
We should write lyrics, and I still remember this song when I was a kid about how to spell chlorophyll that I learned when I was C-H-L-O-R-O-P-H-Y-L-L.
Did you have a game system when you were a child?
I did.
And you chose to do that instead?
So my parents did something that was brilliant, so they didn't get arrested. They made me go to school.
Holy cow!
I know, right? I know. If more people did that, it would be a better place.
Played Xbox or saying about that?
Going to school.
Oh.
Yeah.
All that.
All right. So visual filters. Again, we've sort of talked about this, right? This is basically showing you the magnocellular layer is better at lower spatial frequencies. The parvocellular layers are better at higher spatial frequencies, right? Again, sort of peaking. Now, if we think about this, whoa, who remembers that time I said you're really best somewhere between 1 and 10 cycles per degree? I said that, right? What is the peak for the magnocellular layer?
10.
It's 1. Okay, what's the peak for the parvo?
Oh, yeah.
Yeah, so between 1 and 10, look, you're the best. That's the 2 peaks. You've got the most sort of visual capabilities in that range, right? Isn't that awesome the way that works? It's almost like I planned this slide after I gave you the other one. And I'm just like randomly throwing slides at me. All right, so spatial frequency, we've talked about this in these filters, right? We've said that each layer sort of responds to either higher, if it's parvo, or magno is going to be the lower spatial frequencies, right? Again, if you have a complex image, which most images are complex, you're going to be exciting those receptive fields in both types of layers, right? In the parvo and the magno, so you're going to get everything excited. Now, how do we know that there are these multiple spatial filters, right? Well, we can jab an electrode in your brain, probably not your brain. We can jab an electrode in a brain, right? And we can measure the sort of activity of each of those cells as we present different spatial frequencies, and we go, whoa, this cell, which was in the parvocellular layer, got really excited for small spatial frequencies, but large spatial frequencies, or large bars, low spatial frequencies don't really do anything. And then we go over to a magnocellular layer, and we go, okay, this one got really excited for low spatial frequencies, but high spatial frequencies, I didn't get anything. And that's great, right? But how can we actually sort of do that with humans? And there's some evidence that this happens. I don't want you to think too much about this, but basically what folks will do is they use this concept of like adaptation and masking, right? And so what they can do is they can sort of fatigue one of your systems, right? Sort of like that after image business we talked about. They can fatigue one of your systems and then show you something in that range and you're not as good, show you something in one of the other spatial frequency ranges for the other, either magno or parvo, and you're actually still pretty good at that, right? So they're independently, if you can adapt independently or you can mask them independently, then it's not the same system, right? It's two separate systems. Does that make sense? It's like I can fatigue your red sensitive cones, but I leave your greens and your blues alone.
Is that
right?
like what we did with the lab whenever we had the little filter up to our eye?
It's exactly what we did with color. You can do the same thing with spatial frequency, though, right? Because in that show with color, we have three sort of systems, right? It's trichromatic. We have three separate independent, and we can affect those independently. You can do the same thing with these spatial frequencies. If I were to make you stare for a really long time at a high spatial frequency grating, and then I tried to test you on high spatial frequencies or low spatial frequencies, you'd still do really well on the low spatial frequencies, but the high spatial frequencies you would have some trouble because that system's been fatigued, right? Does that make sense? And again, because I've been baffled by Bill Gates, you'll be able to see that here. If you were to stare at this, it's kind of an interesting phenomenon. Again, I'll get these up on Blackboard for you so you guys can take a look at this. You stare at that dot for a while, these things shift around a little bit, and then they stop. And what happens is it appears as though kind of what's on the top starts to look smaller and what's on the bottom starts to look bigger because, again, you've sort of independently fatigued in two different parts of your visual field simultaneously, either your parvocellular system or your magnocellular system.
Now, how does this, like, I'm not trying to pull away from this, but how does this pertain to real world application?
Yeah, so that's a good question. I think thinking about which systems control visual motion, some of these also, if you think about sort of emotional information, is also handled by one system more than it is the other, right? So if you kind of go back to this picture, can you tell on this particular picture better or worse than in this particular picture?
Worse.
The mood of that person, right?
Oh.
It's a little, it's not as good, right? With that higher spatial frequency, you can determine, hey, she's smiling, right?
Okay.
In the lower spatial frequency, you really can't, right? And so if you want to think about emotional information, you know, it's coming through in that parvocellular pathway, right? So you're getting that information separately than you're getting it through that other system. And I think that's important. I don't know. I've always been interested to know if some folks who have difficulty determining, so here I am like going all the way down to the bottom, right, Josh? If folks who have difficulty determining and responding to the emotions of others, I wonder if they have different visual capabilities.
That'd be so cool.
It would be, right? I don't know that we do.
Somebody should do
It's
it.
quite possible. There are all kinds of other things that are quite possible as well.
That's
But
Yeah.
because different information is coming in through a different pathway, I've always kind of wondered about that, how that works. Yeah, it's actually kind of interesting, right? See, that's pretty good real world. And then, oh, well, here's functional significance, right? So this is not as real world as what, you know, I just told you, but here are a few things. It's really, and we'll talk more about this later. because when we talk about shape and object stuff and we get into some other motion, and here you go, that's a whole, these are actually two whole other lectures. But because you have these different filters, you're able to determine texture and edges, right? And so that's really great. So if I wanted to look at this desk, for example, and I'm looking at this desk and I'm seeing this change in the texture, right? And that's a really high spatial frequency. It's kind of this mottled, dark and gray and white flecks, right? But then I can see a massive change from that to the floor, right? If I only had one sort of filter, right, all of that would look the same, because if I was actually looking at the floor, that's a high spatial frequency pattern as well, right? I wouldn't be able to determine that that's an edge versus just a continuation of the texture. And so having these two filters riding on top of each other can tell you where those breaks are. And we'll explore more about that later when we start thinking about, again, shape and object recognition. Right, Marissa? Don't worry about vernier acuity, right? It's not too big of a deal. Don't have to worry. We'll talk about that some other time. And again, here is just sort of a, we'll come back to this again as we talk about pulling out shapes and objects, right? But here's that basic idea, Mason, where we've got different sort of textures and we can determine that they're edges. And we've got this, it's called a filter, rectify, filter sort of process, where we will filter the image and then sort of go through like a second set of filters, and then we can determine that there are two different shapes there, right? And that's how we pull things out. Again, don't worry about that too much right now, okay? Just want to get the fundamentals of spatial vision. And there's your filter, rectify, filter. We'll come back to that. Again, we'll talk about stereo and motion later. And there are some things you're probably going to forget, but we'll remind you at some point. All right. Questions about that before we move into the lab activity?